iodide ion.
If you take sodium iodide, and iodide is a very good nucleophile, and react it, for instance, with chloroethane, that will give you ethyl iodide plus sodium chloride. Now, I've written the two equilibrium arrows here because obviously you recognize the chloride ion as a nucleophile, which could, of course, come back and undo the process by displacing the iodide ion. So this would be like a tennis match where the iodide ion replaces the chloride ion, then the chloride ion replaces the iodide ion, the ball goes back, and then it goes back and forth, back and forth. What makes this iodide ion a very useful nucleophile is that if you use the right solvent, and that would be acetone, alkyl iodides are soluble in acetone, but alkyl chlorides and bromides are not. So this is a clever trick where if you use acetone as the solvent, as the sodium chloride forms, it precipitates out of solution and it takes it out of the reaction. Certainly slows down its ability to react as a nucleophile, a chloride ion, because it's deposited as an insoluble salt at the bottom of the container. This is actually a name reaction, and I remember it because of the name. It's called the Finkelstein reaction, and I actually had to make a bunch of alkyl iodides using it. It works beautifully. Take a chloride or a bromide reacted with sodium iodide, and your sodium chloride or sodium bromide just plops out of solution, which leaves you with a large concentration of the iodine substitution product. But it's just another example of nucleophilic substitution. So those 6 nucleophiles are all you have to deal with, which would be simple enough, except that the story's not over. There are actually 2 other mechanisms that are totally different. They're not substitution. They're elimination. There's an E2 and an E1, similar to the SN2 and the SN1. Now, how does this happen? Well, elimination, in order to work well, has to work from 2 different carbons that are neighboring. The elimination is actually going to eliminate, in this case, HBr. The bromide ion is going to do its thing as a leaving group, but rather than a substitution by a nucleophile, this proton is going to be lost from an adjacent carbon. It's called a 1,2 elimination or a beta elimination. Now, if you rip out H plus and Br minus, what you're left with, besides HBr, is a carbon-carbon double bond in place of the H and the Br. So by ripping out H plus and Br minus from 2 adjacent carbons, a pi bond appears between the 2 carbons. So this makes alkenes from alkyl halides by a 1,2 elimination of H and Br. The Br is lost as Br minus, and a proton from a neighboring carbon is lost with it, and the organic compound sort of fills in the gap with a pi bond. Now, how does this happen? Well, it happens because all of these nucleophiles that we're looking at are also bases. The hydroxide ion is a strong Lewis base. What's the difference between being a nucleophile and being a Lewis base? It's behavioral. It's what the thing is doing. If a hydroxide ion is attacking a carbon, that's substitution. If a hydroxide ion is pulling off a proton, that's base behavior or elimination. The nucleophile is capable of doing one or the other. And that's true of all nucleophiles. Everything that's a nucleophile is a nucleophile because it's got a non-bonding pair of electrons. Isn't that the definition of a Lewis base? So they're one and the same. It all depends on how it acts in the reaction. And one hydroxide ion can't do both. It does one or the other. But lots of hydroxide ions can diverge, some of them doing substitution, some of them doing elimination, depending upon how the collisions go and the conditions for the reaction and the alkyl halide. Now, we do have animations for those. Let me show you how that works.
I was recording the videos before. I was recording the videos before. I was like, he's like, no fun.
Okay, this is a little hard to look at, but this is supposed to be water. Well, I'm sorry, this is CH3OH, and it's going to pull. I'm going to run the animation again. All right, it's pulling a proton off this carbon, and the halogen sort of drops off as that proton is being pulled off. It's often called a push-pull mechanism. So the hydroxide ion comes in, grabs one of these hydrogens on the carbon next to the halogen and pulls that hydrogen, leaving the pair of electrons behind. That pair of electrons tries to repair the situation by forming a pi bond and, in a sense, kicks out the bromide ion. So the hydroxide ion pulls the proton off, the pi bond forms and pushes out the bromide ion, and you end up with C double bond C. So again, it's a loss of HBr. Notice I have the H and the Br on opposite sides of the plane of the board. That's actually a stereochemical requirement for the transition state. The hydrogen that's being pulled off by the base has to be in the same plane and trans to the leaving group. So it's HBr being plucked off like that. And then the pi bond forms between the two carbons. That's E2, second order kinetics, because the rate would depend on the concentration of hydroxide ion and the concentration of alkyl halide, just like the SN2. It's a one-step reaction that involves one molecule of the base and one molecule of the alkyl halide, so E2. The E1 is where something happens to cause the bromide ion to leave first, so that you have a carbocation intermediate, and then the base comes in a fast step and pulls off the proton to form the double bond. So the question is, when the base pulls off the proton, is the halogen still there, in which case it's SN2, or has it already left, in which case you have a carbocation and it's SN1. The only difference between the E2 and the E1 is timing of the departure of the leaving group. And the same thing is true for SN2 and SN1. Is the leaving group still attached, or has it already left when the nucleophile or the base comes into the picture? If the carbocation is an intermediate, then it's either SN1 or E1. Now, to simplify this a little bit, the E2 and the E1 don't matter because there's no stereochemical difference between them. So nobody cares whether a reaction eliminates, if it's going to eliminate, whether it's E2 or E1. Absolutely no interest whatsoever. With the SN2 and the SN1, yes, we do care when the carbon bearing the leaving group is asymmetric. But for elimination, just understand that it follows the timing difference between the SN2 and the SN1, that is the E2 and the E1, but otherwise it doesn't matter. The real issue is, am I getting substitution or elimination? Because you would never want both. The substitution produces a substitution product. The elimination produces an alkene. If you want elimination, you don't want substitution. And if you want substitution, you don't want elimination. And a lot of the rigmarole in the book is about trying to control that balance between substitution and elimination. Now,